previously looked at chemical equilibria in separate videos looking at the use of K, the equilibrium constant, and also looking at acids and bases, buffers and indicators. Today I'm going to look at chemical equilibria as a whole and the sort of questions that you can be asked. So the things that we'll be focusing on today are reversible reactions and the use of K. A very specific example of using K as the partition coefficient, no longer explicitly in the course, but can be used as problem solving and is also a very useful use of chemical equilibria and K. And then finally, weak acids, looking at Ka, pKa and pH. So let's have a look first of all at the equilibrium constant. So the equilibrium constant is a unitless constant which takes the concentrations of the products raised to the power from the coefficients here in the equation divided by the concentration of the reactants raised to the power of their coefficients. If we look at a specific example here, we have aqueous, liquid, solid and aqueous. Where you have a pure liquid and a pure solid, they get the value of 1. So within the K expression, you don't see those. So a K expression for this reaction will be the 1 product raised to the power of 2 divided by the 1 reactant. You can then put in values for concentrations at equilibrium to find K, or you can use K to find concentrations. Pause the video now and try writing equilibrium expressions for these reactions. So for the first reaction, we have a liquid here, so we're going to ignore that and just write our K for everything else. So always taking care to have the products divided by the reactants. Looking at the second example, all of these are gases, so we don't need to remove anything here. So we'll have SO3 and it's raised to the power of 2, SO2 raised to the power of 2, and then just oxygen. Once you have an expression for K, you can then use equilibrium concentrations to calculate a value for K. So here we have a reaction and some equilibrium concentrations. So first of all, we need our value for K. And then we can insert the values that we have here. So we'll end up with 0.2 multiplied by 0.2 divided by 0.8 multiplied by 0.8. So overall our K value will be 0.0625 with no units. If you were then given information about this reaction being exo or endothermic, you would be able to make predictions about the value of K if the temperature was to be increased or decreased. Here is a similar example for you to try. Pause the video now. So for part A of this question, we have to write out the expression for K. We don't have any liquids or solids, so we can take everything from the equation. So looking at the products first, we have the concentration of CH4, the concentration of H2S, and that is squared, divided by the concentration of CS2 multiplied by the concentration of H2 to the power of 4. For part B, we can then take the equilibrium concentrations at 900 degrees and insert them into the expression to get a value for K. If we then calculate that through, we find that we get an answer of 281. In this question, you're required to work out the equilibrium concentrations before you can work out the value for K. Pause the video now. So the first thing we can do is we can write an expression for K, which is going to be the concentration of PCl3 multiplied by the concentration of Cl2, all divided by the concentration of PCl5. We can then go ahead and try and work out our equilibrium concentrations. So if we take our concentrations at the start, we have 0.100 moles of PCl5 in a 1 litre flask, so that is 0.1 moles per litre, and we have no moles of our two products yet. At equilibrium, we know that we have 0.0420 moles of PCl3, and for every mole of PCl3 that's produced, you would get the same of Cl2. To be able to produce this number of moles of PCl3, you must have lost that from what we originally had, so we can do a sum to work out what is left of our PCl5 at equilibrium. We can then take these values and insert them into the expression that we have previously worked out. And when you calculate that through, we find that we have a K value of 0.030. A specific use of chemical equilibria is that of partition coefficient. This is where you are doing solvent extraction and you're trying to take a solute from one solvent and extract it into another solvent to purify and then to be able to extract it and use it for other purposes. So here we have iodine within an aqueous solution and we are extracting into a cyclohexane layer. You set up an equilibrium between the two layers where only a certain concentration of iodine will be held within each layer, and that is given an equilibrium constant which is called the partition coefficient. So writing a K expression for partition coefficient is the same as for any other equilibrium. We take the concentration of our product, which here is the iodine within the cyclohexane layer, and we divide it by the concentration of our reactant, which is iodine in the aqueous layer. The next part of the question asks us to look at how many moles of iodine we have within each layer. So at the start, we have a certain number of moles of iodine that we can calculate. So we know the concentration and we know the volume of our iodine solution. So if we take those values, we know that at the start we had 0.01 moles of iodine within the aqueous layer. We now know that at equilibrium, we have X moles of iodine in the aqueous layer. If we started with 0.01 moles, then we know that by doing 0.01 minus X, we'll have that many moles within our cyclohexane layer. So we now have a lot of information that can allow us to calculate concentrations. So we have the number of moles of iodine within the aqueous layer and within the cyclohexane layer. We have an expression for K. And we have a value for K. We need to use concentrations within this expression, so we need to divide by the volume of each of the layers. So for aqueous layer we have 100 centimeters cubed, and for the cyclohexane layer we have 50 centimeters cubed. So we now have expressions for concentration that we can insert into here, which will allow us to calculate the concentration of iodine in the aqueous layer. So now we can start inserting values into the equation. So we can take each of the expressions that we now have for concentration and insert them into the equation. We can then rearrange algebraically to try and find x. So by rearranging here by cross multiplying and rearranging for x, we can find that x is 0.0083. So we know the moles, we now need to work out the concentration. So concentration is moles divided by volume. So we need to do 0.0083 divided by our volume, which is 0.1. So the concentration of iodine within the aqueous layer is 0.083 moles per litre. Here's a similar question for you to try. Pause the video now. The first step here will be to write a value for K. So we write that here. So we're going to have the concentration of iodine in the carbon disulfide layer divided by the concentration of iodine in the aqueous layer. So we have that to use later. To be able to use this, we need to know the equilibrium concentrations of both species. However, we only know one at the moment. So dealing with the aqueous side first, we know at the start how many moles we have because we have concentration and we have volume. So we know that we can do concentration times volume to find the number of moles. So that's the number of moles of iodine in the aqueous layer at the beginning. We can then find the number of moles of iodine in the aqueous layer at equilibrium using the same procedure. So we know we have 9.84 times 10 to the minus 5. The aqueous layer is still 0.1. So we know that we have 9.84 times 10 to the minus 6 moles of iodine within the aqueous layer at equilibrium. We still have to have the same number of moles of iodine in total, so we know that the difference between the two must be found within the CS2 layer. So if we take our initial moles of iodine, (2.5 times 10 to the minus 3, and take away the number of moles that we know is in the aqueous layer, then we will find the number of moles within the CS2 layer. We need this as concentration, so we need to do moles divided by volume. The CS2 layer also has a volume of 0.1. So we have a concentration of 0.0249 moles per litre. We can now take the information that we have and insert it into the expression that we have for K. So K equals the concentration in the CS2 layer, which we have worked out to be 0.0249, divided by the concentration in the aqueous layer, which is 9.84 times 10 to the minus 5. And if we then calculate that, we find that the value for K is 253. Another use of K is that of Ka, which is used for weak acids. So if we're to write an expression for K, which is just equilibrium constant, we would ignore the water here because it's a pure liquid. And because this is a special circumstance, we get a subscript A here. However, the process is exactly the same. So we have H3O plus A minus divided by HA. Now, as we know, H3O plus can be simplified to be H plus. We can simplify this as well. So this is an extremely important equation to remember. However, we can use this equation to allow us to generate other very important equations for acids. If we take our expression for Ka, we can manipulate this to allow us to calculate pKa and pH. So if we know that for every H plus we get an A minus, then that means we can simplify this top line here. So we end up with H plus squared. We also know that for a weak acid, the concentration of your HA is going to be almost the same as the concentration that's written on the bottle. So we can substitute that in for C at the bottom. We can then use this to allow us to calculate other quantities. pKa is the negative log of Ka, so another very important equation to remember. If we try and simplify this so that we can get pH, we know that pH is the negative log of your concentration of H+. So if we rearrange this equation here, so that we have H plus is equal to the square root of Ka times C. If we then take the negative log of each side, we end up with pH is the negative log of the square root of Ka times C. Now we can manipulate this using logs to allow us to have terms which are easy for us to use. So what we have here is the negative log of Ka times C to the power of a half. That is the same as us having negative log of Ka to a half plus negative log of C to a half. We know that a negative log of Ka is the same as pKa, so we can take out the negative log and we're left with a half pKa minus a half log C. This is much easier for us to deal with, and we can use this to allow us to calculate the pH of a weak acid. So we have three important equations to remember. We have this pH equation, we have pKa is equal to a half log is equal to minus log of Ka, and we have the expression on its own for K. So Ka is your concentration of H plus multiplied by your concentration of A minus divided by your concentration of HA. So these are the three important terms to remember when looking at weak acids. So here we have a question looking at fizzy drinks which contain carbon dioxide dissolved in water. When you do this, you get carbonic acid, which has a pKa of 6.4. So you're to calculate the pH of 0.1 mole solution of carbonic acid. So using the equation that we've just calculated, so we have a half pKa minus a half log C. So here is your pK, 6.4, minus a half log of the concentration, which is 0.1. So if you calculate that through, you find that you have a pH of 3.7, and this is a weak acid, so a pH of 3.7 would seem sensible. Here's another question for you to try. Pause the video now. So in the first part of this question, we are being asked to write an expression for the dissociation constant, or the equilibrium constant, for hypochlorous acid, which is this one here. So we do this in exactly the same way. We take out any liquids. So we have H3O plus, ClO minus, all divided by HClO. So it's exactly the same procedure as it is for any reversible reaction. I'm going to write that expression here at the side so that we can use it later. So we've been given a value for Ka, and we know that the solution's pH, so we're trying to calculate this ratio here. So from the pH of the solution, we should be able to calculate the concentration of H3O plus. So pH is minus log of the concentration of hydrogen ions. So if we invert our logs, we get a concentration of hydrogen ions as 10 to the minus 5.4. We can then put the values into the equation that we have here. So we know the value for K. We know the value for the H plus concentration, and that is then multiplied by the ratio that we are trying to find. So if we then divide by the concentration of H plus, we should find that the ratio comes out to be 0.01. Here's another weak acid question. Pause the video now. So another question where we're being asked to write the expression for K. We have a liquid, so we can cancel that one out. So we just take our products and divide by the reactants. So we have C6H5 CHOH COO minus multiplied by H3O plus, all divided by the mandelic acid, so there's your expression for K. The same as writing it for any of your reversible reactions. So in the first part of this question here, we're trying to calculate concentration. So we're given a volume and we've got a mass. We need moles, so we can take our mass and divide by gram formula mass to allow us to get the moles of mandelic acid. If you use this formula here to work out the gram formula mass, you'll find that the GFM is 152. So we get 0.0658 moles. We're wanting concentration, so it's moles divided by volume. So none of these sums are difficult, they're all ones that you've seen from National 5 and higher, it's just a combination that you haven't used before perhaps. So we've now got our concentration of mandelic acid. So we're trying to find the pH of the solution. So we know that pH is a half pKa minus a half log C. So C we worked out in the question before as 0.0658. We have Ka, so we can work out pKa as a negative log of Ka. So that is 3.75. So we can now take those values and put them into this equation to work out the pH of the mandelic acid that we're using. And that turns out to be 1.96. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and follow me on Twitter at Miss Adams Chem and Instagram Miss Adams Chemistry for regular updates on new videos and flashcards daily. Bye for now.